All right, well, we're going to work through our seventh lesson in Unit 4, which covers what's called the quadratic formula. Before we get into the actual formula piece, let's talk about why do we need to know the quadratic formula? When is it used? And what does it help us to do? So, when do we use the quadratic formula? We use it anytime that we are solving a quadratic. So, solving, I'm going to put that in quotations. So, solving a quadratic. And the reason that I'm putting the solving in quotations because we've actually done this before. And when we're solving a quadratic, we're solving it when y equals 0. So this happens when y equals 0, and we need to find the x values. And we actually did this exact same thing back when we were factoring. When we were factoring and we were solving by factoring, we let y equals 0 and we solve for those specific x values, which brings us into the next part as to what the solutions or the answers from the quadratic formula represent. They represent x-intercepts. And they represent x-intercepts when the answers or when the values are real. And the reason that that real is important is because if you remember back to what we did on Tuesday, where we talked about the square root of a negative, well, square roots of negative are imaginary numbers. Whenever we work through the quadratic formula and get an imaginary number, it's not going to represent an x-intercept anymore. X-intercepts are only real numbers, so values that are either rational, meaning we can write them as a fraction, or irrational, where we take the square root of something that's not a perfect square. That's most of the time what we're going to get with the quadratic formula. But there are times where we're going to get those negative numbers. Um, and when we do get values that are not real, so when we include that imaginary solution, they're just considered our zeros. So other names for solutions, and let's make note of this as well, that you can see solutions as either being roots, so they're the same thing as roots. They're the same thing as zeros. That's probably the best kind of word for us here because that 0 comes from the fact that we're letting y equal 0 and we're solving for the x value. Okay, so you might see this this question formulated as to find the solutions to the quadratic, find the roots to the quadratic, find the zeros to the quadratic, all of which could correspond to x-intercepts if they are real numbers. All right, so basically we're using the quadratic formula as another tool to solve a quadratic. And again, that's when we're looking for the x values when y is equal to 0. So when we're using the quadratic formula, we're using just the coefficients. And I've mentioned this a few times that the values of a, b, and c, they don't include variables. Okay, a is just the coefficient in front of the x squared. B is just the coefficient in front of the x. And c is just the constant term that isn't attached to any variable whatsoever. So when we're using the quadratic formula, I'm just using numbers. When you see me plug it into this equation, you will never see me plug in an x anywhere because that's what we're solving for, right? Our solution and the number we get by using the quadratic formula is an x value. So your quadratic formula is negative b plus or minus the square root of b squared minus 4ac divided by 2a. Those of you that have done this before have probably heard the quadratic formula song. It's basically a song where they just read out the formula to the tune of Pop Goes the Weasel. In fact, it is on Spotify. You could grab your phone right now and go to Spotify and search quadratic formula, and you're going to find a song that literally reads the quadratic formula. It does exist. So those are kind of the basics to it. Now we just need to work through it. And as you can see, there's quite a bit going on here. So the order in which we perform these matters. Now, as I say this, one last thing of when we use quadratic formula, because of how tedious this process can get, we're going to say that we want to solve the quadratic, but we want to resort to this after we know that we cannot factor. So we use when we cannot factor. Now, with that being said, the quadratic formula will give us these solutions or these roots or zeros or x-intercepts 100% of the time, whether our answers are real, whether they're imaginary, whether they're whole numbers, whether they're fractions, whether they're decimals. The quadratic formula works 100% of the time. As we're factoring, not every quadratic can be factored. So in a way, it almost feels like the quadratic formula should be the only thing that we use when solving a quadratic. And you're not wrong there, but again, the process is tedious, and we still factoring shows up in other aspects, so that's why we still cover it. But the quadratic formula, we are basically going to use that as a last resort when we can't factor a quadratic to find its solutions. And so with that, let's jump right into it. And this is organized where it basically tells us what we need to do as we work through it. So the right side are the steps. I'm going to do that same work on the left side. So step one is to plug in and identify the values of A, B, and C just into the formula right from the start. So in this case, our value of A is 4, the value of B is 9, and the value of C is negative 13. And so using the formula, we're going to say that x equals, or our x values, which again could be x-intercepts if they're real. If not, we would just consider them zeros. Negative b, so that means the opposite number from our b value, so negative 9, plus or minus the square root of b squared, so 9 squared, minus 4, times a, which is 4, times c, which is negative 13. And all of that being divided by 2a, where a is 4. Okay, so step one, we plugged everything in. And notice my use of parentheses here. A lot of this helps us with our order of operations. It also helps if you're going to plug things into the calculator, which I don't want us to go straight to the calculator. We are going to do this in chunks, and we will use a calculator, but I don't want to type this whole thing in because there's so much going on here. And so the first thing that we're going to actually do here is simplify underneath the radical being the square root portion. So I'm only going to work with that square root part. And as I do this, I'm going to figure out a couple things. I know that 9 squared is 81, so I'm just going to deal with that right off the bat. Then we have minus 4 times negative 13. Now, this is often a place where students make mistakes because they're not quite sure how to multiply all these terms and ultimately whether or not we're adding or subtracting this. What I do is I treat this as negative 4. So to me, this is negative 4 times negative 13. And since I have a negative times a negative, I know that I'm going to take this 81 and I'm going to add whatever these numbers end up working out to be. So I always thinking about how many negatives do I see in this minus 4 AC portion. Since there's 2, I know that I'm going to add on to 81. So in my calculator, again, I treat this as a negative 4. And so I'm going to press, and I use parentheses when I'm multiplying, the negative button. Remember, there is a difference between your negative button and subtraction button. So negative 4 times a positive 4 times a negative 13. And that gets me 208. Now, if you treat this 4 as a negative, whatever sign we get tells us whether we are adding or subtracting. But I already took note of that, right? I already made note of that I have 2 negatives here, and thus I should be adding. And with this being positive, just confirms my original thought. So this negative 4 times negative 13 worked out to be 208. So we're going to take 81 and add 208. So 81 plus 208 is the square root of 289. So now we can take the square root and we can get that to be a decimal, but we're going to actually keep our answer exact as possible for as long as possible, and we'll worry about that square root portion. So let's actually change this take square root to say reduce the square root, which is what we worked on in our last unit or last lesson. And so what we need to do is think about, are there any perfect squares that divide the square root of 289? For some of you, you might need to list out every perfect square to be able to identify those. I've worked with square roots long enough that I have them memorized. So what I do is I'm going to take 289 and divide it by what would be the largest possible perfect square that would divide 289. which that would be 12 squared. Okay, 144 is roughly halfway to 289. The next largest perfect square, 13 squared, 169, for sure won't divide 289 because it's more than halfway there. And I can check that. Okay, if it gives me a decimal, it's not going to divide it out, and thus it's not a factor. We want this to be a whole number. So then I start checking 12 squared, which is 144. That's not going to work either. It's close, but not quite there. And I'm going to keep checking every perfect square to see if any of them divide them. And it's perfectly possible that there aren't any perfect squares that divide 289. So next up would be 121, right? That's 11 squared. Let's just double check that. 121, so 289 divided by 121. Again, I get a decimal that doesn't work. So 289, 100. I know 100 won't work. I'm going to skip that. What about 9 squared, which is 81? That doesn't work. What about 8 squared, 64? I don't think so. What about 7 squared, so 49? No, so we've done 9, 8, 7. What about 6? So 6 squared or 36? No. 5 squared, 25 for sure doesn't divide 289 because it doesn't end in a 0 or a 5. 4 squared, 16. No. 3 squared, 9. Maybe. No. You know what? I don't think there's any perfect square that divides this. The only ones that we have remaining are 4, and 4 definitely doesn't divide it. So basically 289 is as reduced down as possible. We cannot divide any other perfect squares from that. So step 2 is done. We reduce the square root. And now I want us to rewrite what we've done this far. And what we've done is we've only simplified underneath the square root, making our equation x equals -9 plus or minus that square root of 289, all divided by 2 times 4 in our denominator. This is the place where we can actually do that multiplication. So now we need to split into 2 equations. And the reason that is because it's plus or minus. Anytime we take square roots, and we talked about this back when we were converting forms and actually graphing quadratics in vertex form, we need to have an equation where we're going to add the square root and one we're going to subtract the square root. So that's x equals -9 plus the square root of 289, all divided by 8. And then x equals -9 minus root 289, all divisible by 8. And so after we've done this, we've split the 2 equations, simplified the numerator. Well, we can't do anything else, right? We could if we convert these to decimals, but -9 plus the square root of 289, we can combine. So what I want us to do at this point is make a note that these answers are exact. We literally cannot go any further in terms of simplifying these answers. But what we can do, and where this is going to be helpful, is what if we needed the x-intercepts here? And I asked us, what is the value of each x-intercept here? Well, I couldn't even tell you off the top of my head what -9 minus the square root of 289 divided by 8 works out to be. So what these last few steps are going to have us do is what this said originally, take the square root. This is going to give us a decimal and a rounded value of this x value. So let's still go ahead and figure out what the decimal version of our answers are as well. So now I'm going to actually take the square root of 289. Which is 17. Oh my gosh. I should have kept going with my perfect squares. The fact that it works out to be a whole number actually completely changes this problem. Anyways, we still would continue with this process. So -9 plus 17, all that's going to get divided by 8. Then we have -9 minus 17, all of that's going to get divided by 8. And so this is incorrect now. Those are not exact because the root 289 is a perfect square. And so now we're going to simplify the numerator, or the top of both fractions, by doing the adding or subtracting. So -9 plus 17, that's 8, giving us 8 divided by 8. And then -9 minus 17 is -26, and that needs to get divided by 8. And so then 8 divided by 8, that's 1. And then -26 divided by 8, let's see what that is, -3.25. So x equals -3.25. Could also write that as a fraction. So I could go math, enter, and write that as a reduced fraction -13/4. So basically, through the quadratic formula, these are our exact answers, and they're rounded. There was nothing to round them to, but because these are real numbers, these are the x-intercepts. So let's make a note of that. These are x-intercepts, which are also the solutions to the quadratic. So in parentheses, let's say there's the solutions as well. Solutions, when they're real, are x-intercepts here. Okay, well, we're going to do a couple more examples with this. Again, the place that we're going to have the most issue is with this square root and reducing it whenever necessary. I guess this also brings up a good point that we should always just check if that number is a perfect square like what we had here. But regardless, we're going to do the exact same steps. Okay, so we're going to do this exact same thing again, and we're going to do it twice. So for this one, let's have you follow along again. And then in number 3, I'm going to ask you to pause and work through that one on your own before you check it with me. Okay, so right back from the beginning, let's pretend like we're doing this for the first time again, where we are going to start by plugging what our values of A, B, and C are. So A in this case is 10, B is 2, and C is 4. And so I'm going to plug those values into the quadratic formula. So x equals negative b, which is negative 2, plus or minus the square root of b squared, so 2 squared, minus 4 times a, which is 10, times c, which is 4. And then all that gets divided by 2 times a, where a is 10, so 2 times 10. And so the first thing we're going to do is simplify underneath the radical, or simplify the square root. So again, I'm going to write that off to the side. And the reason I do that, just so I don't have to rewrite the rest of the equation. So I'm just writing the square root where I'm going to take care of that 2 squared and call it 4. Then I have minus 4 times 10 times 4. Now, I mentioned this last time that I'm very thoughtful about what my sign's going to happen here and whether or not I'm going to add to this 4 or subtract. Right now, I see 1 negative. So when I do 1 negative times 2 positive, that's going to result in a negative still. So I'm expecting to take 4 minus some value. And so now on my calculator, again, I treat this 4 as a negative. So I go negative 4 times 10 times 4, and I get negative 160, telling me to subtract 160 from the 4. So this is the square root of 4 minus 160, which is the square root of negative 156. Well, this is imaginary, right? We cannot take square roots of negatives. And the next part of this, yes, we're taking the square root, but really we need to reduce this down. And so the first thing that we're going to do is the fact that this is a negative, we're going to take that negative away and call this root imaginary. So I square root of 156. And now I'm going to see if I can't find a perfect square that divides the square root of, or divides 156. Just so we don't run into the same thing as last time, let's just make sure that 156 is not a perfect square, which it's not. And now again, the starting point, it can't be more than halfway. So halfway to 156 is like 75, 80-ish, right? So the smallest perfect square that could potentially divide 156, let's start with like 8 squared or 64. Or even bigger than that, 81, I'm sorry, would be a better one. So I'm going to see, can I divide 156 by 81? And it doesn't quite get there. It gives me a decimal, so I just keep going. So my next one, I did 9 squared, so 8 squared, so let's try 64. Nope, get a decimal. How about 49, 7 squared? Nope, get a decimal. How about 6 squared, 36? Nope. How about 5 squared, 25? I know for sure it's not 25 because that doesn't end in a 0 or a 5. How about 4 squared, so 16? Maybe actually. Almost, not quite. How about 3 squared, which is 9? I don't think so. No. And then the last one, so that was 3 squared. We have 2 squared, which is 4. Maybe, yes. Okay, so the only perfect square that divides 156 is 4. So I'm going to factor 156 to be root 4 and then root 39, where root 4 is 2. So this square root simplifies to be 2 root 39, and then it is imaginary. So this is 2I root 156. And so now, this is why I do all this work on the side. See how much work we had to do there to ultimately do the negative or the b squared minus 4ac and then simplify that? Now I can take this simplified term and resubstitute it back into the equation rather than having to rewrite all that other stuff 1, 2, 3, 4, 5, 6 times. So now we have the fact that x equals negative 2 plus or minus 2I root 156 all over 2 times 10, which is 20. Okay, so we have reduced the square root. Now we're going to split into two equations and say that x equals negative 2 plus 2I root 156 all divided by 20. And then x equals negative 2 minus 2I root 156 all divided by 20. And you know what? That is the exact version of our answer. So this is exact. And because it's imaginary, these values are not x-intercepts. And because they're not x-intercepts, it's not even worth our time to figure out the decimal value because we can't plot those. Okay, all this tells us is that these values are the solutions to this quadratic, which they do have value in more complex applications that deal with quadratics. Nothing we're going to do in this class. But for what we're thinking about with quadratic formula and getting x-intercepts, with these being imaginary, they are not x-intercepts. So we are done here. Okay, this is our simplified solution. They are exact. There is nothing more that we can do. And again, these are not x-intercepts because of the imaginary number there. Okay, as we move forward, let's keep, unless we are specifically graphing a quadratic and need to find the x-intercepts, let's just keep our answers exact. Converting them to decimals is just more work. And again, the only reason that we would ever need to do that is if we're trying to find the x-intercepts, which we're not doing that right now. The whole thing, what I want us to work on is find the solutions. So I'm going to ask that we do number 3 on our own. So I'm going to ask that you hit pause and work through this to the best of your ability. I did take away the steps here, so you have to try to not look at the steps I did above. Unless you get stuck, then you can refer back to those. But we want to see how far can you get on your own without having to look at those notes. Now, one quick thing before we jump into this. This equation looks different, right? We're missing something. Typically, it's ax squared plus bx plus c. And I'm looking at this. I don't see an x, so there's no b term. But we can add that in by saying 6x squared plus 0x minus 10 equals 0. So now a is 6, b is 0, and c is negative 10. Go ahead and use those values, plug it in the quadratic formula, see what you come up with, do your best to reduce your radical, and then go ahead and unpause the video once you've worked this out completely. All right, so with the b value of 0, it does simplify some pieces. It also allows or puts us in some situations where we have to be like, okay, what is that 0 doing? It doesn't matter. Anyways, the negative b, so the negative 0, that does nothing, right? Adding 0 does absolutely nothing. So that whole part we don't need to write in there unless you really want to, but it doesn't make any difference because adding the 0, there's no value to that. So then I'm like, okay, I've got 0 because 0 squared is 0. Then minus 4 times a times c. I'm noticing I have two negatives, so I'm expecting this value to be added and thus positive. And negative 4 times 6 times negative 10 is 240. The largest perfect square that divides 240 is 16. So factoring out a 16 and 15, I can then take the square root of 16 to get 4, and the root 15 is left over. So root 240 simplifies to be 4 root 15. That makes the quadratic or the results to our quadratic formula plus or minus 4 square root of 15 divided by 12. So that's positive 4 root 15 divided by 12 and negative 4 root 15 divided by 12. And again, we will leave our answers like that. Now again, this is the exact form of our answers. Because they are real, these also represent x-intercepts, if we went ahead and found the decimal version, which again, we don't need to do, but just to show you real quick, 4 root 15 divided by 12, okay, it'd be about 1.29 if we were to go to graph this. And then negative 4 root 15 divided by 12, negative 1.29. So we get plus or minus 1.29 as our x-intercepts if we needed to graph them. But again, let's just leave our answers exact. Even on the homework, just leave them exact for as long as possible. Okay, well, if you need more help, I would encourage you to Google quadratic formula. You will find a number of videos. If my video didn't work all that great for you, go to YouTube, find another video on the quadratic formula. You can find endless amounts with various explanations. So please be willing to do that if this wasn't all that helpful for you. Have a great day.